Good morning, everyone, and good afternoon to those who are out there in Europe. We are very happy to welcome you to the fourth webinar in the series for the JAM 7006 project, looking at stable isotopes in the Rio Bueno sub-WMU of the Dry Harbor Basin. My name is Jeffrey Marshall, and I'm the Chief Hydrologist of the Water Resources Authority. It's a joint project between the WRA and the International Atomic Energy Agency. This webinar will be culminating the putting together, so to speak, the information that we've looked at in the previous three webinars, looking at stable isotopes in precipitation, stable isotopes in groundwater, surface water, and remote sensing and drone photometry in karst areas. So our presentation this morning will be a joint presentation by the two experts who have been working alongside the WRA with this mission. And that's Dr. Aurel Persoy and Dr. Christos Penos. Both gentlemen are here and ready to go. We thank you for your patience. And without further ado, I'll hand the virtual lectern over to Aurel and Christos. Gentlemen.
Thank you, Geoffrey, for the introduction. And thank you all for being here. As Geoffrey said, this is going to be some kind of summary of what we've been doing over the past few months. So it's not gonna have anything new information. Basically, what we are doing today with Christos is that we are putting together the conclusions of the previous studies, and we are putting this into the context of the original proposal that the Water Resources Authority made. And we want to show where we are, what results have been obtained, and more important, how these results can be used to help manage the water in the Rio Bueno area. And also, basically, this is kind of how this study, this management study by the Water Resources Authority, can be further expanded so that other catchment areas or other similar areas should be studied based on this as an example. So we have a presentation. It's a common presentation. We will be doing it together. I think I will start the discussion and then Christos will take over because we have different parts, different expertise and so on. And then the conclusion is mostly, so we hope that the conclusion of this presentation will be a discussion. So we would like basically to throw up some ideas and then some questions and then see how this can be, how this study and how this project can be further developed. Okay, I will start. I will share my screen and then let's see how it is. Where we are. This is it. Okay, this is minimized. I don't need this. Let me put it aside. Okay, just a second. Oh. Play from start. Okay, I hope it's visible and I hope the pointer is visible. So let's start.
Yeah. No, we're not seeing it.
Good, thank you.
No, we're not seeing the screen.
You don't see it?
No.
Okay, let me do it again. Do you see it now?
Yeah, we're seeing it now. Okay,
good. So this is the introductory slide, and here it is, the title of the proposal, and on the right side of the screen you see this what we devised as a conceptual model of this study with the three interlinked how to say, not study areas but focal points. Number one being the atmospheric processes, and then the second being the processes on the surface of the ground, and third being the underground processes in the karst system. And here is the cross section, which basically is the same as this on the right. So we have the processes in the atmosphere, And then we have the processes on the surface before infiltration of the water. And then we have the inside, the inner part of the Karst system with the different components, the flow, then the conduits linking the surface to the ground, linking the input points to the output points. And during our let's say assessment of this proposal and ideas and the data that we had, we were discussing 3 main points. And one was that we have this weather and climate variability and change. And by variability, I mean this short-term variability, year-to-year change, or maybe decadal or less than decadal, whereas by change, I think the long-term multi-decadal 20, 30, 40 years change. And then these are important because these are the basic framework, one of the basic frameworks for water availability, because the water is derived ultimately from precipitation, and this will change both with short-term and long-term changes. And whereas the short-term variability is important for the day-to-day availability of water, the long-term change is very important for the planning, because if some of the management tools are planned, these are supposed to be in place for the next few years or even decades. And in this case, we have to keep in mind how the climate will change during these decades. And the second, let's say, starting point or underlying the fixed point for this water management is the bedrock and karst topography. And these are somehow fixed for the time scale that is under consideration here, years to decades, but it is extremely important to understand what is happening both at the surface and both in the karst, in the underground. Because depending on these, we have I put this word hectic because this is sometimes the truth in karst areas. We have a hectic recharge of the water in terms of timing of the recharge and the recharge patterns, and also the flow dynamics, because we have this very heterogeneous karst system where water flows both through pores and also through conduits. So it is very difficult to understand when we compare it to the normal Darcian flow in porous media. So it is very, very important to have a very good knowledge of the surface topography and also of the karst, the underground karst, the cave conduit, the conduits, and basically the caves that are underground, because these are sometimes the main avenues for water transfer from the surface, from the ponors to the springs. And then the third point is the pollution, because this is very, very important, especially that this is both an agricultural and industrial area. So this water contamination is a major issue in karst areas, again, because of the different type, because the flow of water through karst is different than from porous media, and natural attenuation of pollution sometimes is it's less than is expected. Basically, it's a conduit that is, it's a pipe. Karst system sometimes are pipes that are connecting the inflow to the outflow, and sometimes, or most of the times, there is no natural attenuation of pollution between the input and the output. So karst water pollution, it's a very important topic as opposed to, let's say, porous media, normal media. So these are the keywords that we identified. So we have water availability, we have hectic dynamics, and then we have contamination. And if I remember well, the proposal by the Water Resources Administration was related to one of the development goals, sustainable development goals of the United Nations. And this is ensure availability and sustainable management of water and sanitation for all. And you can see we have this availability, water availability, and we have the sustainable management. And here it is important to understand the recharge timing and patterns and the dynamics of the flow. And then we have sanitation, which is linked, of course, to the contamination. So the entire presentation from now on will be in this context. Basically, we will be discussing how we use and how can be further use the stable isotopes to study all these potential problems: availability of water, contamination of water, and also flow dynamics and water recharge. And not only stable isotopes, but also surface morphology, especially linked to photogrammetry and the use of drones as proposed by the water authority. Okay, so here it is in green, what we've been doing. We've been using stable isotopes in precipitation to study these changes. We've been using stable isotopes in surface and groundwater to study this. And then Karst processes studied for this topic and also for this topic. Okay, so let's start. First is I will be moving through this from precipitation through waters and karst and end with the pollution. So this is initially what we did. We were looking, we looked at the the isotopes in precipitation to identify the source of to start identifying the source of the water and the processes that can be linked to changes in the atmospheric circulation patterns that can be further traced into changes in water availability. We only had data for half year, but we were, again, I know it's not maybe the most appropriate to say fortunate because it was a tropical storm and it had a strong impact on the life of people and the property, but this offered us the opportunity to get some data that maybe it will not be possible to obtain the next few years. So one of the issues that is related to this water availability is that we are living in a time of changing climate, and this is the projections for the next few decades. And you can see that Jamaica sits at a point where it is not very sure how the climate, how the water, how the precipitation will be in the future, in the next 20 to 30 years. It's at the limit between a climate that will be definitely drier, but it could be drier and more variable and drier and less variable. And this is an important distinction because depending on the capacity of karst to absorb precipitation water, the same amount of water that is delivered in a short time, it's could result in less available water in the springs because the karst has a limited capacity to absorb this water. So most of it will be lost, to evaporation or surface runoff. So it is very, very important to understand how the karst area is being recharged, how long does it take, what are the processes to recharge these karst areas, because these will allow to adapt to any change in the future, whether it will be more variable or less variable, meaning the same amount of precipitation in a 1 month or throughout the year. So it's very important to understand how this water gets underground. And this is the entire data set. And you can see that in black, it's the precipitation water that has been collected between March and August 2021. And the red crosses are the precipitation that has been collected by Geoffrey during Tropical Storm Grace on an hourly basis. And you can see that most of the precipitation water between March and August is concentrated in this area, the black dots, whereas this event, Tropical Storm Grace, the waters are extremely depleted in both both oxygen and hydrogen heavy isotopes. So it's totally distinct signature. And this is important because you will see further that we were able to trace this impact of tropical storm on the surface and the groundwaters. Here you can see the average values for the different water bodies that have been investigated. Black is precipitation. We have the wells in green, we have the springs in brown, and the sinks in yellow, and in blue is the rivers. So they are distinct. We can distinguish between the two. Later we can go into more details and we can see this differentiation between sinks here in yellow and the springs in brown, and this difference between the two likely indicates either a delay in the transfer between the springs and between the sinks and the springs, or different contribution of base flow and high water flow, or in Karst processes like mixing and things. These are the point that needs further attention. I will show you later on. And here, just to emphasize the difference between the precipitation between March and August and the tropical storm grace, completely different values here in red. And you can see this is the precipitation values for August, again influenced by the monthly precipitation values in August in red that were influenced by tropical storm grace as opposed to the previous one. So the difference is too large to be simply explained by the fact that it was a different month. Theoretically, one would expect that the values in August would be higher than the values between March and July, whereas here they were much more depleted by 10 per mil, perhaps, which clearly indicates the strong influence of one single tropical storm. And then hopefully this year, there will be no tropical storm, no cyclone effect in Jamaica, and then we will get a completely different data set that we will allow us to compare the two, a year with a tropical storm, a year without a tropical storm, and then we can use this data to further assess how these extreme events are affecting the storage of water and the transfer of water to the underground and the dynamics of underground waters. We will see. So yes, here is just the data. You can see the annual variation here in the monthly variation for the 3 stations for precipitation, and you can see here the drop in the values during August, which were influenced by grace. And the wider context, I've collected here data from several stations nearby. I'm showing the same chart that I've shown a month ago, maybe, just for consistency. As you can see that precipitation in Jamaica fits more or less with the data from the surrounding area, but not completely. So it is important to develop a local, these are a local meteoric water line for precipitation in Jamaica, so that this will act as a baseline for any future studies. It is, even if they look almost similar, they are quite different. So especially if one wants to study how the surface waters and groundwaters relate to precipitation, then it is important to have local data, because you can see, for instance, here in blue, you have data from Havana, from Cuba, and here is Jamaica. And if you study surface waters or groundwaters, it is important whether they fit here, because if you use Havana as a proxy for Jamaica, and you get surface water somewhere here, you could say, oh yes, of course, they are there on the local meteoric water line defined for Havana. But if you look at this difference between Havana and Cuba and Jamaica, then waters that would plot here, they are completely different than the precipitation waters. So even if looking on taking a wider perspective, you would say that generally this is the same climate, this is the Caribbean climate, the same type of precipitation, the same time of climate variability, the same type of precipitation patterns. These slight differences are important, and they help better understand and put into context what is happening with surface and groundwaters. And the take-home message, the two main lines that we consider that are important for analyzing precipitation waters is, first, that we need a long-term perspective, and second, there is a high uncertainty related to the extreme events. And by extreme events here, we mean tropical storms or hurricanes affecting areas. So these are the two important messages that we think emerge from our investigation of our study of the precipitation data that has been collected in Jamaica over the past year. I will use a similar type of discussion for the next slides. So I will be briefly discussing the surface waters, isotopes in surface waters, and then go to the take-home message, and then move to Karst and the take-home message, and then we will be discussing the pollution, and then the use of epic methods, and again the take-home message. So when it comes to Karst vulnerability assessment, Just a second. Here, I think Christos will be discussing this. I'm not sure.
Yep.
Should I use
Yeah.
my screen or do you want to switch to your screen?
It's okay if we can continue with your screen, because then I have to upload the presentation, etc. So it's okay. So yeah, for my part, we are going to discuss about the Karst water vulnerability assessment and what is important to be done. So now, Aurel, I would like you to press the button. So in order to achieve something that it is quite accurate, and it will give us, will provide us with reliable results, the first thing that we need to do is to constrain the catchment. So a precise catchment delineation is really important. And in order to do this, since we know that the karst catchment is not always the same as the surface water catchment area, so it doesn't coincide all the time, every time. So what we need to do is to do geological mapping, surface mapping, take advantage of any well data or springs, caves, and maybe tracing that we have done in the area. And by using the term tracing, I'm referring to both artificial tracing, but also natural tracing using natural tracers, such as the stable isotopes that Aurel is talking about. So we should take advantage of all of these, use all of these criteria to delineate an accurate catchment area. So yep, and the end result should be something like this, like a catchment area, a groundwater catchment area that doesn't coincide with the surface, with the superficial catchment. So I just made this as an example. It doesn't, it is not accurate, but what I wanted to show with this drawing here, with the catchment area that I drew here, is that it doesn't fit at all with the one on top. So that's why it doesn't follow the slope or the ridges or whatever on this map. Okay, next. And then after we managed to define our catchment area, it is crucial to define, to use as accurate as possible parameters to define the epic, the vulnerability of the catchment. So the tools that we need for this is actually the values that we have to define are epicars, protective cover, infiltration, and karst. So the underground karst. In order to define the epikarst, the superficial karst, we will need an accurate DTM plus fieldwork. So this accurate DTM might be it might be the result of drone photogrammetry, photogrammetry in general, or we might acquire the DTM by any other source, like some different agencies that they might are giving high resolution DTMs, or they are giving them for free, or we can buy those DTMs from different agencies or companies that are producing DTMs. For the protective cover, so this can be the results this can be the result of a work and the input by data that we are getting from various sources, plus the field work. So as I saw you in the last seminar that we had, the last webinar that we had, we can define the protective cover either by going on the field and making real field work and taking measurements of the thickness of the soil, etc. Or if we want a better and faster assessment of this value, we can use indirect methods such as using maps, vegetation maps, or land use maps, or whatever we have in our disposal. But it is better if the optimum would be to combine both of these methodologies. The optimum in terms of time and precision of our work. So in order to reduce the time, we can use such data as I said before, from different GIS sources, and some ground truthing will help us define or being more accurate on what we are, on the values that we are getting. As far as it concerns the infiltration, there we can use again the DTM to extract the drainage network, or accurate topographic maps, or field work again, or we can also use high resolution satellite images or aerial photographs. Again, we can acquire aerial photographs from drones or different other sources. And of course, to have a good knowledge about the bedrock geology of the area. So I mean, in some areas, it is possible that we get some drainage network developed, but that bedrock might correspond to a and into an aquiclude or a bedrock that cannot be karstified, so it cannot add to the karst groundwater. And finally, to have, as Aurel also mentioned before, and he will actually talk about it later on, to have a good knowledge about the karst of the area. And by this term, I mean the underground karst, and this is actually we are referring actually here to the caves of the area, or at least the big conduits that are from which the water is traveling into the underground. So in order to know that, we can either perform field work and explore and map caves, or in areas that or for teams that they are not so used to doing that, we can use literature or get in contact with local caving clubs, etc. After when we define this, we can actually use this data to generate maps. So Aurel, can you, by using the EPIC equation, the one that I have on the bottom of this slide, and our end result will be something like this. So it is a really bad graphic here, so excuse me, but different colors corresponds to different values. And in the areas where we have most of the colors that are overlapping, we have the most prone to most vulnerable areas in our catchment. Okay, next. Yeah, again. So the take-home message for the karst water vulnerability assessment is the precise determination of the catchment. This is really crucial, and the high resolution of the layers that we are going to use for qualification of the EPIC parameters. So these are the two things that we need to keep in mind all the time to determine the catchment in a very precise way, and to use as high resolution layers as possible to for defining the EPIC parameters. So Aurel, I think it's your turn now.
Yes, I will. I will continue from here, and I will show how stable isotopes can be used to partly address these two issues. So yes, I will continue with this slide. So this is the study area, and here I plotted just two schematics of the surface morphology. You see it here with the evolution of cockpit karst on the right, and here the recharge types. And you can see that we can have different types of recharge. The simplest one on the left with point recharge here, input and output. And we have a more complex one with several input points. And these are concentrating to form an output. And then we have the third, where we have diffuse infiltration over a larger area with not a very clearly identified inflow. And then all these are merging together to emerge as a spring. And very likely, most of the karst areas, and I guess also this area here, the cockpit karst area, the Rio Bueno catchment, is a combination between these two, with several input points and also with diffuse infiltration. As you can see it here on the right, so you have this, just think of this river that is sinking somewhere here into the karst, and also the underground karst is also fed by diffuse infiltration that is happening in between these conical hills. So it is very important to identify the area. It is easier for the input points because basically you just consider the catchment area of these points, but it's very difficult when you are thinking about the diffuse infiltration that is happening in between these conical hills that are separating the cockpits. So here it is important to use tracing. And this is an image that photograph that Geoffrey took. I think it was in August, and I like it very much because it shows the, just a second. Sorry, it's my kids. I'm home alone with them. So this shows the bottom of one of these cockpits, and you see during periods of heavy rains, there is accumulation of water on the surface, and very likely that at least part of this water will get underground to feed a system like this one. So it is important to know how much of the underground, how much of the water that emerges from the spring is coming from this kind of infiltration, and how much is coming from point infiltration, like river infiltration or like a ponor, because then this has very important implications for the recharge mechanism, the type of recharge, and what kind of water will get underground. For instance, if you have a like tropical storm Grace was last year, this will dump a huge amount of water in between the hills on the surface of the ground. And depending on the capacity of the karst to absorb this water, you will have more or less water getting underground. So these also need to be, as Christos said, mapped and considered for the feeding of the water. So yes, this is the kind of data that needs to be put together in order to get the information that I was talking before. And I think this the photogrammetry and the usage of the drones that was envisaged by the Water Resources Authority can offer this kind of information. And also now there is data available from the Sentinel-1 satellites that are offering maps of surface moisture. And if you look at the availability of data, there are the satellites, the Sentinel-1 satellites are passing overhead every area every 2 or 3 days. So it is possible just by measuring the soil moisture in a specific area to get ideas of how fast this moisture disappears. And by combining these satellite-derived images of soil moisture with information on local weather, then it can be estimated how much water is being lost to evaporation and how much water is getting underground. But for this, you will need these the high-resolution DTM, and you will need the local data, drones and photogrammetry, and then the data from the satellites. Okay, so this is the take-home message related to the karst geology and morphology, a precise mapping of surface features, because this can this This will help identifying of the input points, and not only the input points like here, but also the input areas like here. So this is important to be studied, the surface morphology of the karst area. And I think with this I will move into the isotope parts for this one, and the investigation of surface and subsurface waters, like these waters here, some of them. And again, I will start with with this chart that shows the different types of waters. Again, black is precipitation. Sinks here in yellow, this is the average value of all the sinks that have been sampled by Geoffrey and his team, and the wells. And by wells we mean just these deep wells. And then in brown is the springs in the same area, and the blue is the rivers. And I will change to a different type of presentation. Here you can see the temporal evolution for some of them. I didn't plot it all of them. I put some just for illustrative purposes. In all 4 charts, the blue-green colors, so these 3 are showing precipitation at the 3 stations. So this blue, this green, and this, what color is this? Is this magenta? Purple. So these 3, the blue, the green, and the purple, are precipitation. And you can see the variability of precipitation with slightly lower values in March, increasing trend towards summer, and then the outside effect of tropical storm Grace in August. And this is where we were fortunate. This chart will show how fortunate we were. So I will start with the wells. You can see the variability of precipitation. And you can see here the wells, they were not affected at all. So the very, very stable values throughout the year. And here you can see that tropical storm Grace had no influence on the isotope stabilizer composition of water in these wells. So this could be either that the infiltration was not enough time between the precipitation in August 2021 that occurred, I think, towards mid to late August 2021, and the sampling of the wells was done towards the end of August. So it was a 1-week period between the actual precipitation and the sampling point. So that means that either the wells are not affected on the short term by processes at the surface, or the response time of wells is more than 1 week. We will see once we will have the results from September and October. If in September or October we see a drop in the delta values, that means that there is a delay time of maybe about a month. Or if you see it in October, there is a 2-month delay. Or if we don't see, that means the mixing in the epikarst is very effective, and there is no long-term influence of the surface of extreme events on the water of the wells. And this has important implications for the management of the waters, because then it can be discussed how is the water recharged and how long does it take from the surface and so on. This is not what was true for the wells is not true for the other waters. You can see the rivers were influenced. So the 2 rivers that has been the 3 rivers that have been analyzed, one of them stops here. They seems to be relatively constant throughout the year, and here you can see that in August they responded to the changes in the delta values of the precipitation. So the delta values of the rivers dropped, and this is somehow expected because you have quick surface runoff and also the direct precipitation in the water. So it is expected to see the signal of tropical storm Grace in surface rivers. The same is true for sinks. Here you can see with dotted lines the sinks that have been analyzed. The same kind of response as we see here, a drop of about maybe 1.5 per mil in August. What is interesting is that the springs, which are discharging the karst areas, show a similar response, and this is even higher than it was in the sinks and the rivers. So that means that the water that is feeding the springs is not only water that is entering through the sinks or the ponors, but there is also very fast infiltration of surface water. So if I can go back, so very likely a large amount of the water that has been sampled in the springs was coming from direct infiltration on the surface, like this type of infiltration. So not this point infiltration on the rivers, but everywhere here on the surface of the karst. And this is important, as Christos said, for identifying the recharge areas in order to further study the pollution of the aquifers and the storage of the water. So here, if I move to the next one, you see the values of the sinks here and the values of the springs here. And this difference between the input and the output indicates, in my view, that the tropical storm Grace had a strong, the recharge of the karst aquifers that are discharged to these springs had a strong input of water, direct infiltration on the surface, not only the ponors, but surface diffuse infiltration on the entire karst area that sits above the springs. And then it is very, very important to identify exactly this recharge area. It could be on the surface, to correspond on the surface to the area between the ponor and the springs, but it could also extend laterally through many kilometers. So it is important to identify this type of this recharge area, how large it is and where does recharge happening. Like here is the map, the spring. So we have to know for every spring which is the recharge area, whether these are disconnected, like every springs has a distinct recharge area, or rather, based on the morphology of the karst and the general hydrology of cockpit karst, whether here we are talking about the large area that acts as a recharge area for several springs, and all these springs are discharging not at one point, but an area like this one is discharging through several different springs. So this is something that needs to be investigated in more detail, and then so that we will know exactly whether we have this type of recharge or this type of recharge. So it is important, the take-home message, sorry, for this type using isotopes, that we need to identify the transit times, and we need to identify the cave processes, because to do so, we will need to use not only this type of tracers like stable isotope tracers, but also chemical tracers, or like fluorescein or salt or things like this. And also it is very important in order to understand the discharge, what is the residence time in the underground. This will partly be addressed just by looking at several of the next samples that have been collected in September and October and November, to see if this drop in the values, in the delta values that is related to the influence of tropical storm Grace, will recover. How long it will take? It will take a month, it will take 2 months, but then it is important to use radiometric dating methods to understand both the age of the base flow, so this water here, and also to check, and then to check what is how this influences the outflow during extreme events like this one. And this requires, this transit time determination using tracers and dating methods, radiometric dating methods, and also identification of cave processes. And this is again important. And by cave processes, I mean to study the type of flow in the caves, the type of passages, how these passages are these flooded constantly, is flow happening in completely flooded passages, what is the vertical extent of the karst, by karst I mean of the caves, what is the vertical extent of the epikarst above it, and so that we can know how much of the water is flowing through base flow and how much is flowing during high water stands, and how much water can the karst accommodate. Because depending on how much water can accommodate, much of it is possible that some or much of this surface water will simply not be able to infiltrate, because it will exceed, the amount of water will exceed the saturation potential of the karst. So this is also this is why it is important to understand what is happening in the underground. Okay, so we will with Christos we put together some I would say final charts. So again, here on top, I've plotted these three issues. You know, the availability of water related to climate variability and change, and then the flow, the water flow, and the dynamics of the flow, and the recharge related to geology and the topography of the karst, and then the contamination of the water. And here below we put the 4 groups of take-home messages. These are the same as previously. So we need and here is how we see the links between them. We have the precipitation study, which will give us an idea of what is happening in terms of general water availability. And then we have the karst geology. And this is important to understand the recharge of the aquifers, the dynamics of the flow. So here it is, this one, yes. And also the same karst processes are important for contamination of the water, for the study of water contamination, because these are influencing how water is flowing underground. And depending on how water is flowing underground, we know what is the potential for natural attenuation of pollution. And then we have the study of the use of stable isotopes, tracing methods, and dating methods, radiometric isotopes, to study the surface and subsurface waters. And this is important for the recharge of the aquifers and also for the contamination. And then finally, in order to study the contamination, we have this EPIC method for karst catchment vulnerability. And this will give us a more precise understanding of the contamination of the water and how water is contaminated and what is happening once the contaminants are getting underground and are reaching the springs at the other end of the karst system. So I think this is our final slide, and I just did it like this. Yes, exactly. Yeah, the source of pollution. Yeah. So we would be happy to discuss further with you and then take your questions and hopefully have some, if not answers, just some ideas of how to further continue this. So thank you.
Okay. That's it. All right. Thank you very much, Aurel and Christos, for that comprehensive presentation. We'll now open. If you have questions, and anyone in the audience has any questions, you'd like to raise your hand, and we will unmute so you can ask your question. I do want to acknowledge the presence of one of our former managing directors, Mr. Herbert Thomas. We're really glad to see you on here, sir. Okay, Shanti Prasad from JBI. I see your hand. Please go ahead.
Yes, I found the comments on the storm events quite interesting. Is there an ability to say if the recharge occurs at an accelerated rate?
I don't, I'm not sure. So if I may share again the presentation. So yeah, maybe this one. So here with these, so the input is here in blue. So these two are showing the sinks, the pond, and here is the output, the springs. So I don't know. It is evident that the water at the springs was strongly affected by the water that was dumped there by Tropical Storm Grace. Now, if I remember well, the date of Tropical Storm, the passage day was August 17, and the sampling was done between August 25 and 28. So let's say it was something like 10 days between sampling of precipitation and sampling of the springs. So there was ample time for water to get underground, and to feed the springs. And by seeing the fact that the sinks have a lighter, weaker signal from the storm, and the springs have a larger one, I mean, theoretically, one would expect that if it's only the sinks, here is the input, then the output would be less because it's mixing with the water that is already stored down there. But the fact that we see this, the springs have a larger signal than the sinks, that means that there is a large amount of water was transferred to the underground by this surface infiltration. So the entire surface area, the entire catchment area was acting like an infiltration area. What we don't know, and I'm not sure if we can do it like this, is to understand how fast this transfer is. How, if it, as you said, if it's like accelerated or not. I don't know. It would be very interesting to study this with tracers, like just during an event like this. Not, it doesn't necessarily have to be a tropical storm. It just has to be a heavy rain, just to leave, just to put you know, these tracers, like, I don't know, fluorescein maybe in this water here, and see how long does it take to get to the karst, to the springs, and then it can be also measured. The, you know, it's not only qualitative, but it can be also be quantitative.
Right. So just a follow-up. What we've noticed in some of the meteorological data is that at the end of the year, more or less total rainfall is not varying very much. But when we have a storm event, the intensity, and this is part of our climate change manifestation, we get a lot of rainfall in a very short space of time, and then we'll have several months of drought and so on.
Yes.
So I think, you know, the general modeling of the karst is interesting to move it to the next step, to understand the phenomena of how these climate variations are going to impact the environment.
Yes, this is exactly, that's I mean, that's the important thing, because you can see, for instance, the future models are saying that the entire area will become drier, but they are not sure whether it's become drier or more variable and drier and less variable. And as you said, you have the same amount of precipitation in 2 consecutive years, but in 1 year you can have a extreme event that will dump a huge amount of water. And the important question is, how much of this water will get underground? Is there a difference between the water that gets underground during when you have a, let's say, a more uniform distribution throughout the year, so you have a constant rain and constant infiltration, or if you have the same amount concentrated in a few rains, is the karst capable of absorbing all this water so that you will get the same discharge in the springs? So this is one of the most important questions, I think, here. And this you know, to do so, you will need a lot of assessment of the karst processes and what's with the karst, what are the specifics of the karst there in the area.
Right. So just one final comment. I also deal quite a bit with air quality. And one of the things that we have been looking at is the Sahara dust phenomena. And I'll raise it here because that will also bring a different set of chemical species, as well as perhaps some pathogens and so on. So the idea of the relationship with contamination, obviously in the case of a dust cloud, you will have that basically blanketing the whole watershed. Perhaps it's not as fine-tuned to be able to determine those quantities, but certainly, you know, the phenomena of acid rain and so on, it's something I think in the future we will become more and more refined in assessing.
Yeah. Mm-hmm.
Okay, thank you very much, Shanti, for those incisive questions. There's a question in the chat from Natalie Ferguson, another past employee of the WRA, asking, are the influences of geological faults being considered as they play a role in the movement of water through the aquifer to the springs? Movement of groundwater through the karstic aquifer would add value as well. to respond to that?
Yeah, at
Yeah.
this stage, we didn't look at this data because we didn't look into that much detail. I am. Yeah,
Can you hear me?
yes.
Yeah, but usually, I mean, the geological faults or any other discontinuities, they are favoring karstification. So where a former, let's say, geological fault is developing, probably karstic aquifer or corridor will follow that same direction, etc. So in that sense, I mean, I think that dealing with caves and working with caves partially also covers this, not partially, but in actually in quite big extent covers this, let's say, this the problem that the faults might introduce into our modeling.
Yeah.
So yeah,
Basically,
I think yeah. Yes, sorry, Aurel.
I just wanted to, say that in Karst, every fault is also a conduit for water, basically.
Okay, that's noted. Because going to that conduits point, Shanti says she disagrees a bit. It's more the formations themselves. But you mentioned artificial tracing, because one question I wanted to ask, come in, Shanti, in the sense that we have done some artificial tracing before, where every sink that is placed on the program for monitoring has been traced to a river outflow. One or the other has been traced to that. And when we did the tracing originally a few years ago, none of them came out in the springs per se. I don't know if it's because of distance or maybe it was a lag or something. But how would the isotope data help to account for that distinction where you have the proven connection from the sinks to the rivers, but not yet from the specific sinks to those specific springs that we've measured so far? How would that come out in the data that we've collected thus far?
Yeah, it's ideally one would combine the two of them. So the best would be to have transit times for base flow and also transit times for high flows, because this would be very different. It could be that during high flows it could be much faster, but depending on the characteristics of the karst, it could also be much slower. And also it is important that, especially during periods of high flows, it's the water that feeds that ultimately gets to the spring is not only water that is entering, like here on the left, you see. So this is the ideal, but basically what you have is a combination between these two, the type B and type C, where you don't have only one single sink. You could have maybe 2 or 3, or you can have maybe 1, but definitely there is a strong influence of infiltration that is happening directly on the surface. So yeah, isotopes in combination with tracing.
Okay, so I see that for future work, maybe in this year going forward, we can begin to look at more dye tracing as on top of the isotopes that we're doing.
Yeah.
Shanti has a follow-up. So you're saying? Okay. Shanti has a follow-up. I'll allow her to.
Yeah.
Yes. I might have been a little bit disingenuous with my comment to Christos. What it is, we do have different limestone groups. And I think this area that was studied, it is a bit of degraded karst. So in between everything, we do have some plutonic inliers, not in this specific area. But the faulting doesn't seem to be overly controlled by the karst itself. We do have some connectivity to this amazing fault plane that carries us all the way to Haiti, the Plantain Garden Enriquecillo fault. So, I mean, it is a nation because of the geological volcanism and so on. It may be that the two act as separate controls for the infiltration. So the evolution of the karst itself is quite irregular, I would think. And I think, you know, these comments that you really do have to do the field work, you have to do proper characterization. Absolutely, that will give us the best approximation for how to trace the outputs and so on from the limestones.
Yeah, I don't disagree, but I mean, as a general rule, usually karst follows these pre-existing fractures or whatever. I mean, in that sense, this is what that's why I replied like this. But yeah, I mean,
Okay.
I mean, the fault connectivity is an issue. Yeah, of course. But usually karst will give us an input on these things, like actually the other way around. Fault connectivity might give us a hint about karst development and karst geometry. So yeah, I don't know. Yeah, as I said, fieldwork is the key on this.
Fieldwork is key indeed. All right, we see Oliver asking you to give your input now.
Yes, okay. Yeah, I'm not too deep into these, let's say, tectonic discussions about Jamaica, as we are all, of course, not all, means Aurel, Christos, and me, not so familiar with the local geology. I think it will be an important aspect for the project now to put together. That means, in a way, Geoffrey and his team needs to work on this, but together with the experts, an overview to link these features. So we need maps, and those we have to combine because probably they don't exist, that show both our sampling points at the moment and, for example, the fracture system, and maybe other geological features. I think that's what, for the project point of view, we not currently have. You for sure have it in the Water Resources Authority, but we, for the project, don't have this overview at the moment. Bringing together the sampling point and sampling strategy with the different geological features. So would you think that is something we can work on for the next weeks or next months?
I agree. That information is here. The publications that Shanti is speaking of, the knowledge that's there. We have the fault system set up and everything. So while we haven't been collecting the data in a vacuum, it's a matter of having the results now, putting it together with the geology and hydrostratigraphy that we already have a knowledge of. Again, tied with the information that we did with previous dye traces, so that would guide our future exploration to see, okay, having seen this historically, having seen this isotope data now, where can we go between drone photometry and high flow artificial tracing to see what's happening? Like I said, once we knock heads with the data we have thus far, we can see better where to go and for analyzing and future research in the upcoming months. And we're looking forward to doing that, because this data so far has been really interesting. And I think it'll provide a good base for ongoing and future investigations. Indeed. All right. Are there any further questions? We've been here for about an hour. All right. If there are no further questions at this time, I would like to thank Aurel and Christos for their contributions in the 4 presentations that we've had. This is most likely the last for now of the webinars. We will be meeting again, as in the project technical team, to determine the steps forward. Data collection continues. We should be shipping off the last quarter's worth of samples sometime this month, and we're continuing to collect for at least another year, as in up until March of next year. So there'll be a lot more data to analyze and to provide information and guidance. Thank you all for your support over the past couple months with the webinars. We have recorded them. They will be uploaded to our YouTube page at some point in the future. And we hope that you will continue to support the work in whatever way you can, and to be benefited in water resources management of Jamaica and its karst hydrogeology, I should say. Thank you very much again, and have a great rest of the day.
Bye.
Thank you.
Thank you. Goodbye. Thanks a lot.
You.